Welcome to the remediation video for the last unit. The last unit that we did, we covered molecular polarity, intermolecular forces, and then how intermolecular forces determine the physical and colligative properties of substances and solutions. You've been identified as somebody that needs to do additional remediation on this material as indicated by your answers to the questions on the test. Notice that questions 65 and 66 and 72, 73, we're looking at your understanding of molecular polarity and your ability to draw on polarity arrows. And then those remaining questions, 67 through 71 and 74 through 79, were an indication of your understanding of the rest of the material as listed here. So it is important for you to understand molecular polarity and how to draw in those polarity arrows. Understand that you will not be expected to draw Lewis dot structures, as we've already remediated that in a previous unit, but you will need to be able to not only draw in polarity arrows, but also figure out which molecules are most polar if you're comparing to by looking at electronegativity differences. And then you also need to be able to relate polarity to the following physical properties. So you need to be able to figure out how polarity indicates intermolecular forces, the phase of matter that a substance will be in, whether it be a solid, liquid, or gas, whether that substance is volatile, which means that it evaporates easily, the temperature at which it would boil, the strength of its adhesive and cohesive forces, and then also whether or not that substance will dissolve in water. This is going to be the order in which we're going to cover these subjects, and so we are going to start first with molecular polarity. As we discussed in the unit, the first step in identifying molecular polarity is drawing a Lewis dot molecular structure. As I mentioned, we're not going to have you do this in remediation. We will give you the Lewis dot molecular structures. Once you have the Lewis dot molecular structures, in order to figure out the polarity of the molecule, the first thing that you'll do is draw in the polarity arrows for each one of these bonds. You'll find that in order to do that, what you will do is look up the electronegativities for those elements, and then you will draw the arrow towards the atom that is most electronegative. Then once you figured out the polarities for each one of the bonds, you then need to determine if the molecule is polar. Now, in order to do that, it comes down to a question of symmetry. Symmetry means that a molecule is balanced or the same all the way around. And if that's the case, it means that all of the different the polarities of the individual bonds cancel each other out, and the molecule as a whole is not polar. And that can be confusing, so let's talk about how to make that more simple. So when you're trying to identify whether or not a molecule is symmetrical, what you need to remember is that molecules will be non-symmetrical, non-balanced. Molecules will be non-symmetrical if they have one of these two things true. One is if they have different atoms around the outside. As you'd expect, if there are different atoms around the outside of the molecule, they won't balance each other out. That molecule will be non-symmetrical. Another thing that can make molecules non-symmetrical is if they have unbonded electrons on the central atom. Now, if either one of these things is true, if they either have different numbers, different types of atoms around the outside, or if they have unbonded electrons, they will be non-symmetrical. And if that's the case, they'll be polar. And what you will do then is draw a polarity arrow towards the most electronegative atom. Now, if neither of those is true and the molecule is symmetrical, it will be nonpolar, and you'll just label it as nonpolar. So keeping these ideas in mind, let's look at some examples. So the first example that we have is CCl4. And if you look at CCl4, that is a horrible color. If you look at CCl4, you'll notice, first of all, that there are chlorines all the way around the molecule. So that would tend to tell us that this molecule would be symmetrical. But we've got to look at one other thing, and we look at the central atom, and we notice that the central atom does not have any unbonded electrons on it. These two things together tell us that this molecule is symmetrical, and therefore it is nonpolar. So now let's look at another example. Up here in the right, we have a carbon dioxide molecule. Thinking about test number 1, we notice that these two outside atoms are both oxygen. That is a pass of that first test then. Then we look at the second test, we look at the carbon, and there are no unbonded electrons on the carbon. We don't have any of this. We don't have any unbonded electrons there. And because those are not present, we understand that that molecule passes both of those tests, and it would also be symmetrical and therefore nonpolar. So now let's take a look at this example down in the lower right, left-hand corner. So now we take a look, and question number 1, are the outside atoms the same? And of course the answer is yes, these are both hydrogens. But now you'll notice if you look at the central atom, which is oxygen, now we have unbonded electrons on that oxygen. These unbonded electrons make the molecule non-symmetrical, and that tells us that this molecule is polar. So now what we've got to do is we've got to figure out what direction that polarity arrow goes. So what we need to do then is we need to look up the electronegativities of these atoms. Oxygen's electronegativity is 3.44, hydrogen is 2.2. That tells us that the oxygen is stronger than the hydrogen, meaning that this bond is polar in that direction. Notice that we draw an arrow towards the most polar atom, and we cross the other end, telling us that the right side is positive and the electrons move in the direction of the arrow towards the stronger atom. Now here we also have a hydrogen with an electronegativity of 2.2, so that bond is also polar towards the oxygen. Understand, though, that these are not the arrows that you need to be able to draw in order to figure out the overall polarity of the molecule. The one that you've got to be able to draw in is the one that is the sum of both of these. So what we've got is we've got an arrow moving to the left and we've got an arrow moving up, and the sum of to the left and up is an arrow that is moving up and to the left, and so the red arrow represents the overall polarity of the water molecule, and you'll notice that the arrow points towards the most electronegative element, which is the oxygen. So now we've got another example. Here we've got NH3. I would imagine that your eye is immediately drawn to the fact that we've got unbonded electrons on the nitrogen. The minute you see those, you know that that molecule is not symmetrical and therefore polar. So now that we know this molecule is polar, again we need to draw in the electronegative, or the arrows that represent the polarities of the bonds. Hydrogen all the way around is 2.2. Nitrogen, on the other hand, has an electronegativity of 3.04. That means that all three of these bonds are polar towards the nitrogen. So now what we need to do is we need to draw in the overall polarity arrow for the entire molecule. And we've got moving left, moving right, and moving up, and the sum of that is simply moving up. And so the polarity arrow for this molecule, again pointing at the most electronegative element, nitrogen, goes from top to bottom. Now we've got kind of an interesting example. We've got hydrogen and chlorine. So now we don't have a central atom. So how do we know whether or not this thing is polar? Well, notice that hydrogen and chlorine are not the same atoms. So looking up their electronegativities, hydrogen's 2.2, chlorine is 3.16. That means that this bond is polar towards the more electronegative chlorine. But that bond is the only bond in the molecule, so that also tells us the polarity of the molecule. The entire molecule is polar towards the chlorine. Finally, then, looking down here in the bottom, you'll notice that we've got a molecule that does not have unbonded electrons on the central atom. So if we look at that molecule initially and say, hey, there's no unbonded electrons on that central carbon, we might be thinking that that molecule is symmetrical and therefore not polar. But now you'll notice that hydrogens are not oxygens. So now we have different atoms around the outside, and these different atoms make this molecule polar. So again, oxygen has an electronegativity of 3.44, hydrogen's 2.2, and then carbon, I believe, is about 2.55. So now drawing in the polarities of these atoms, this is polar. Let me keep with my colors. This is polar in this direction, this is polar in this direction, and this guy is polar in that direction. All of those bonds pointing at the strongest atom. And now we've got moving down and to the right, up and to the right, and to the right, and the overall trend is moving towards the right. So that molecule, again, is polar towards the most electronegative element, which would be the oxygen. So now that we have an understanding of how to identify the polarities of molecules, we now need to talk about, for the rest of this video, how that changes the behavior of these molecules. So what we're going to do is we're going to take a look at a couple examples, and then we're going to look at how these molecules behave differently based upon their polarities. So here we have CH4. Again, notice that all of these atoms are the same, and there are no unbonded electrons on the central atom. So what direction does the arrow go in this molecule? I hope that you see that it doesn't have an arrow because this molecule is symmetrical and therefore nonpolar. Now we come over and we've already established that water is not symmetrical. Notice that it's got unbonded pairs on the oxygen. That means it's not symmetrical and therefore polar. And as we said before, it is polar towards the hydrogen like so. So now that we understand that CH4 is nonpolar and water is polar, we can now talk about how these substances behave differently. So first of all, we are going to talk about phases of matter. So if we take CH4 and we get a bunch of these molecules together, each one of these molecules is nonpolar. These molecules do not have attractions for one another. Remember that the attractions between polar molecules are called IMFs, Intermolecular Forces. And you'll notice that these molecules are not polar. Because they're not polar, they do not exhibit intermolecular forces. They do not attract each other. As a result, these things are gases. Remember that these little triple dot dudes here are the mathematical representation for the word therefore. So the logic goes like this. These molecules do not have polarity. Therefore, they do not have intermolecular forces. Therefore, they are gases. Now let's take a look at water. We established a second ago that water is a polar molecule. I'll do my best to draw some of these in, but fear this isn't going to go well. But these molecules are each polar. And when these polar molecules get together, what ends up happening is the positive end of one pole attracts the negative end of another pole, and these guys end up attracting each other, positive to negative, negative to positive, all throughout the system. And this creates what we call intermolecular forces. These intermolecular forces are not bonds, they're weak attractions, but they're important attractions because they determine the phase of the substance. So you can see that in water, these polar molecules, their dipoles, all attract each other. The polar molecules attract each other. And because these are polar molecules, they therefore do have intermolecular forces. And as a result, these things exist as liquids. Now, as we talked about in class, this continues on. If you have even more polar molecules, their intermolecular forces will be even stronger, and they will tend to be solids. But understand, we're not expecting you to be able to tell the difference between what will be a liquid and what will be a solid. We simply need you to understand that substances without intermolecular forces tend to be gases. Substances with intermolecular forces can either be liquids or solids. So this then brings us to the difference between the phases. If you remember from the diagram in class, we have solids, we have liquids, and we have gases. And you'll notice from the diagrams that the particles inside of a solid are definitely attached to each other. They have intermolecular forces. But in addition to intermolecular forces, they also have a very high degree of structure. They're locked in place and they're very well structured. Looking at liquids, these too have intermolecular forces, but you'll notice that they do not have structure. Instead, their positions are random and these molecules are moving all over the place. And then finally in the gases, these things do not have intermolecular forces, and consequently their locations and behavior are even more random. So as you're thinking about how to compare solids to liquids to gases, it becomes a question of structure and intermolecular forces. So as a solid becomes a liquid, the structure breaks. As a liquid becomes a solid, the structure forms. When a liquid becomes a gas, the intermolecular forces break. And when a gas becomes a liquid, the intermolecular forces form. So you will then need to be able to relate the strengths of these intermolecular forces to whether they're solids, liquids, and gases. But it's also helpful for you to understand what happens when these things change. All right, so skipping slides now, we're going to jump down here. And now we're going to talk about something else that you need to be able to do with this idea of polar molecules. So, uh-oh, that's the wrong slide. Wow, I went way too far. Just a second. There we go. Okay, so we've now established the difference between polar and non-polar molecules, but what happens if you have two molecules that are both polar? So if we take a look at a molecule like H2S, we can look at this and determine that this thing is going to be polar simply because we have unbonded electrons on the central atom. Looking up their electronegativities, we find out that hydrogen is 2.2 and sulfur has an electronegativity of 2.58. That tells us that this bond is polar, this molecule is polar in that direction. So I'll redraw that for us. Actually, I'll just let the computer draw it. We know that that molecule is polar in that direction. Now, as we come over here and take a look at water, we've already established that water is polar like this. So now we have two very similar molecules. They look the same, they're polar in the same directions, but the question is, do they behave the same as it comes to their polarity? And the answer is no. These molecules do not have the same polarity. So how do we know which one is more polar? Well, the answer is this. We look up their electronegativities. And in order to figure out their relative polarities, what we need to do is figure out how polar these bonds are. So in order to figure out how polar these bonds are, we need to do a little math. So let's take a look at water and let's figure out how polar the bonds are. So oxygen has a polarity of 3.44 and hydrogen has a polarity of 2.2. So if we do the math and subtract, we find out that this bond has a polarity of 1.24, and so does this one. But now coming over here and looking at the hydrogen sulfide, if we subtract their electronegativity differences, we find out that this bond and this bond both have polarities of 0.38. We find those by subtracting 2.58 minus 2.2. So what we see then is that the bonds in water have a polarity of about 1.24, the difference in electronegativities. Hydrogen sulfide's 0.38, the difference in electronegativities. What that means is that the bonds inside the water molecule are more polar, making water more polar. So water is more polar and H2S is less polar compared to one another. So then the question becomes, how does that affect things? What is that? How does that change things if water is more polar than H2S? And so as we begin to look into this, we find out that all of the other things that you need to understand, including volatility, boiling point, adhesive, cohesive forces, and whether or not things dissolve in water, all hinge on the polarities of these molecules. So, for example, let's take a look at volatility. So volatility is a measure of a substance's ability to evaporate. So in order for a molecule to evaporate, what we've got here is a beaker full of water, and these gold balls represent any molecule. For now, we'll say that these represent water molecules. So each one of these then is an H2O molecule. So in order for this to evaporate, these molecules have got to be able to break free and jump out of the beaker. Well, the thing that's keeping them from breaking free are these forces of attraction that are represented by these arrows. So, in order for this water to evaporate, these forces of attraction, intermolecular forces, have got to break. Well, what we just established is that water is very polar. Because water is very polar, its intermolecular forces are strong. These intermolecular forces then, represented here, are hard to break. That means that this doesn't evaporate very well, so it has a low volatility. Now, if we play that same game with H2S, we know that H2S is less polar. Less polar molecules have intermolecular forces that are easier to break. Because those are easier to break, that happens more easily, and this substance will evaporate more easily as well. And all of that can be summarized like this. Molecules like water have high polarity. Therefore, they have strong intermolecular forces. Therefore, they have low volatilities. So, for example, this would be water. Highly polar, low volatility. Now, compare that with this relationship. Molecules with low polarities, like H2S, have weaker intermolecular forces, as represented by the downward arrow, and they have higher volatilities. So H2S would evaporate more quickly than would water. So now moving along to the next property that we need to understand, boiling point. And you'll notice that the picture is the same. The same things that determine how a substance will evaporate determine how it will boil. So again, if we're talking about water, we know that these forces are strong. If those forces are strong because water is highly polar, they're going to be hard to break. In order for water to boil, those forces have got to break, and because those forces are strong in highly polar water, they'll be hard to break, and water has a high boiling point. So it goes like this. Highly polar molecules like water, therefore, have strong intermolecular forces. Therefore, they have high boiling points because they're hard to break apart. Now, if we talk about something like H2S, H2S is less polar. That means that these intermolecular forces are weaker, they will break more easily, and the boiling point of water, or of H2S, will be lower. So low polar molecules like H2S will therefore have weaker intermolecular forces and will therefore have lower boiling points. Finally, relative to physical properties, the next one, the last ones that we need to talk about are adhesion and cohesion. To remember the difference between these, I like to remember that adhesive is glue. So glue sticks two different things together. So this is outside of the substance, sticking two things together. Cohesion is within the substance, sticking it to itself. So, for example, if we look at the meniscus in a graduated cylinder. Here we have the graduated cylinder with the water in it, and if we zoom in over here on the left, we've got the glass molecules over on the left here, and then we've got the water molecules. Now these glass molecules are polar, the water molecules are polar, and these water molecules are being drawn up the side of the glass. That is an example of an adhesive force because it's glass to water. Now cohesion's a little different. Cohesive forces are actually the forces that allow things like this to take place. If you look really closely at the end of the bug's legs, you'll notice that they're making indents into the water. The water has a skin. That skin is actually what is called surface tension. What happens is these polar water molecules are attracted to each other, and as they are attracted to each other, they create a film, and that film actually can support the bug. Now, these are water-to-water forces, so they are within the water, and that would make them cohesive forces. Okay, so we've got one more thing that we need to talk about. We understand this relationship. We'll wrap this up and then we'll talk about our last thing. We understand that highly polar molecules have strong intermolecular forces and therefore strong adhesive cohesive forces. It's the top. Oh, it's no, anyway. And then low polarity molecules have low intermolecular forces. It's actually the bottom. And they have weak adhesive and cohesive forces. Okay, so let's wrap up then. The last thing that we need to talk about is how polarity affects solubility, whether or not something will dissolve, and also how it affects the boiling and freezing points of solutions. So let's talk about this first. When we look at water, we're looking at our beaker on the left. And when we look at water, we remember that water molecules are all attracted to each other through intermolecular forces. And these intermolecular forces have to be broken again to get a substance to boil. Now, we now need to talk about how solutions form. You'll notice on the right, the middle and the right, we've given you pictures of salt water and also sugar water. So first of all, let's talk about how solutions form. So we remember that water molecules are polar. And these polar water molecules are strongly attracted to other polar things. Those things could be ions, like the sodium and chlorine in salt, or they could be molecules like sugar. But regardless, what happens is these polar water molecules are attracted to these polar substances, and the intermolecular forces that exist between the water molecules and the salt ions stick these things together and allow the salt to go off into solution. You'll notice with sugar water, it's very, very similar. That here we've got a sugar molecule, and these polar water molecules are also attracted to the sugar molecule, and that allows the sugar to dissolve in the water. Now, what if we put something in water that is not polar? If we put something like sand into water, sand is not polar. And because sand is not polar, the water molecules are not attracted to it, and it will not dissolve. So fundamentally, anything that is polar will dissolve in water, and the more polar it is, the better it will dissolve into the water. So if we've got this idea that polar things dissolve and non-polar things don't, the question then becomes, how does that affect the boiling point and the freezing point? Well, what happens is this. We established a second ago that water molecules are attracted by intermolecular forces, and in order for that to boil, those forces have got to break. And the temperature at which the water boils is determined by how hard it is to break those forces. The stronger the forces, the harder they are to break, the higher the boiling point will be. Well, if we come over here to salt water, we know that the water is attracted to the salt. But we know that the water is strongly attracted to the salt. And because the water is strongly attracted to the salt, those intermolecular forces are stronger. Because those intermolecular forces are stronger, they're harder to break. Because they're harder to break, the boiling point goes up because the water is harder to break free because it's strongly attracted to the salt. Well, the same thing happens in sugar water. All of these sugar molecules are surrounded by water molecules. These water molecules are strongly attracted. If they weren't, the sugar wouldn't dissolve. Again, in order to get the water to boil, we've got to break those forces. But because those forces are stronger, they're harder to break, and the boiling point goes up. So adding sugar, adding salt to water makes the boiling point go up. The more that you add, the higher it goes up. So what then about the freezing point? Well, the thing that we need to keep in mind in order to understand this is that in order for water to freeze, it has to break free of any contamination. So when salt water freezes, the salt does not get caught up in the water. When sugar water freezes, or in the ice, when salt water freezes, the salt doesn't get caught up in the ice. When sugar water freezes, the sugar does not get caught up in the ice. So in order for water to freeze, these water molecules have got to break free and then come together in order to form a salt crystal. And so that's pretty easy to have happen over here in pure water, because these molecules aren't attracted to anything else. They freeze pretty easily. They freeze, as we know, at 0 degrees Celsius. Well, the problem is if we look over here inside of salt water, we now know that these molecules are all attracted to the salt. And because they're attracted to the salt, it's harder for them to get together and form a crystal. And as a result, the freezing point will be below 0 degrees Celsius. Same thing happens in sugar water. The water is attracted to the sugar. Because it's attracted to the sugar, it has a harder time getting together, and the freezing point goes down there as well. So there you have it. Those are the things that you need to know in order to be ready for the remediation. You have a letter in front of you explaining to you how it is you'll proceed from here. Remember that what you needed to do is take notes over this video, and then you also need to now print the assignment that is posted along with this video. You need to complete that assignment, check your answers, make sure that you're doing this correctly, and you need to bring all three of those things: your video notes, and actually two things: your video notes and your completed assignment. You need to bring that to Mr. Knappenberger's room either on Tuesday, January 24th or Wednesday the 25th, and you will be doing a remediation session during Pride. Doors close at noon. If you're late, you either missed your opportunity to remediate or you're just going to need to come back on Wednesday. If you don't bring either of those items, you will also not be admitted. During the Pride session, we'll go over this material again, answer questions, make sure you've got everything figured out. You will then receive another assignment to make sure that you fully understand what you're doing. The answers to that assignment will be posted on our website as well. Once you've got that assignment completed, you will then bring that assignment with you on Thursday, January 26th, and you will have the opportunity to take the replacement test. That will be at 2:30 on Thursday the 26th, and that will be in your teacher's room. Remember, you need to get 80% on that replacement test in order to have your original test score raised to a 75. The invitation letter that we gave you is actually your release to Pride note. Please write your name on there and then bring that with you. And we actually will be collecting these letters from you, or checking for these letters as well when you come in on either Tuesday or Wednesday. So thank you for taking the time to go over this. If you have other questions, please make sure that you get with your teacher and get those resolved. And we look forward to seeing you Tuesday or Wednesday that would be Tuesday or Wednesday the 24th or 25th. All right, take care.